So, you want to do face recognition, but why? Could it be that you're a teacher? Or even the principal, with hundreds of students ushering in the school in the morning? As tedious as it is, attendance is taken for each student in each class by hand. Couldn't we just take attendance when they come in? Or be it that you're a farmer with a large herd of cattle. It could be a pain to remember everything about each of them. How easy could it be to approach a cow, take a picture of it, and have its name, birth, age, and health displayed right on a screen? Finally, imagine you are a police officer attempting to discover a missing child. Sitting through millions of hours of CCTV footage in search of one child is akin to looking for a piece of hay in a haystack and highly impractical. But what if we could get a computer to do it in a matter of minutes? Well, there are various other reasons why you would want face recognition, but how does a computer actually do it? Well, think about it. How do we do it? Perhaps if we understand how we accomplish this feat, we could replicate the same in our computers. We have evolved a whole area in our brain dedicated to recognizing faces, known as the fusiform face area. What this area helps us do is essentially helps us recognize some recurring patterns such as some unique features of a face and then compare them. The unique geometry of each feature of a face is known as a nodal point. But what is a nodal point exactly? Well, it could be the width of your nose, the distance between your eyes, distance from forehead to chin, or even the shape of your jawline. The human face has an average of 80 nodal points, of which almost all are used as nodal points keep changing as you grow. But how do computers actually detect and locate those nodal points? Neural networks are the answer. Unless you live under a rock, you've probably heard of them, but you might be wondering, how do they actually work? What is inside that little black box that causes it to do whatever it does? Assuming absolutely no background or prior knowledge, I will show you what a neural network is and what it does, not as a buzzword or some jargon, but as a piece of math. I've compiled my journey to understand how neural network works and visualized how a neural network structure is intuitively motivated. By the end, you will undoubtedly understand the logic behind these neural networks. As the name suggests, neural networks are inspired by the brain. The network is basically a bunch of neurons connected together, like our neural network. But what are these neurons? There is something that hold a number, between 0 and 1 to be accurate. The network starts with a lot of neurons corresponding to the input image, each of them holding a grayscale value for each pixel of that image. Basically, they hold a number that tells us how dark each pixel is. For this example, the network
starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these neurons make up the first layer of our network.
Now the last layer has two neurons, with each of them representing a face that the input image could be, which you want to compare against. They also hold a value between 0 and 1, and the neuron with the highest value is the neuron chosen by the neural network. But you might be asking, why layers? Why do neural networks even have layers, and how can we hope layers to recognize faces? When we recognize faces, we piece together different nodal points and the geometry. Recognizing a nodal point can be broken down into subproblems. A way to do this would be to first recognize the edges that make up the nodal point, which could be made up of various smaller lines. So, maybe when an image of a face comes in, the neural network lights up all the neurons associated with around some 100 edges that correspond to the edges of the face in the image, which in turn light up the neurons associated with the nodal points, which finally outputs the closest face the image might be associated with. So the goal is to have a system that can combine pixels into edges, edges into nodal points, and nodal points into faces. To better understand how it works, the hope is for one of the neurons in the second layer associated with detecting edges should actually detect edges. The question is, what dials should you be able to tune to get that neuron to capture that very specific edge in that very specific region? To begin with, the network must in fact have those set parameters. So, we will assign a parameter called weight to each connection between our neuron in the second layer and all the neurons from the input layer. Weights are as numbers. Remember when I said that each neuron corresponds to a pixel in the input image? What we can do is set all the weights of all the neurons to 0, except the neurons that correspond to the pixels in the region we care about. Now that the weights have helped us capture this edge, multiplying the weights with the neurons and then adding all of them together will sum up to adding up the values of the pixels in the region we care about. Because the weights outside the region are 0 and multiplying with 0 results in 0. And also because adding 0 to the sum has no effect on the sum. So all we will get is the value of the edge we just captured. Now we have just captured some activated pixels, which may or may not be an edge. If there really is an edge there, the pixels around it will logically be darker than pixels in the region we just captured. Because an edge is just a line at the boundary where the activated and dark pixels clash. So by assigning negative weights to the neurons that correspond to the pixels above the region, we ensure that the neuron is most activated when a narrow line of pixels is lit up, with the pixels above the region are dark, which is basically the definition of an edge. Now, if this is really what a neural network does, is a question I will come back to after we know how a neural network trains to recognize faces. But you have gotten an understanding of why neural networks are structured this way and why we can expect them to work. Also, if you're wondering what the initial weights of each connection are, they're initialized with some random values which are then later trained and optimized to capture whatever the neuron is supposed to. Anyway, once this weighted sum is computed, the result could be literally any number which knows no bounds. So how would we be able to determine if the neuron even gets activated? Theoretically speaking, we would need some sort of a function that takes the weighted sum of that neuron as input and then outputs if the neuron at hand is activated or not. To put it in another way, an activation function that outputs a boolean value which is either true or false. This activation function is known as the step activation function and is somewhat analogous to how in a biological network of neurons, either the neuron would fire or simply it would not. Now, when you tune the weights, ideally we want it to lead to a change in the activation of that neuron of the same magnitude of the change we just made in the weights. This change could be towards the desired output or away from it, but it should be measurable nonetheless. So what we want is that a small change in a weight leads to a small change in the activation of that neuron. Or in other words, the changes in the activation of that neuron should be proportional to the changes made in the weights. Now let's look at how the step activation function decides if a neuron gets activated or not. It is one of the most simple yet naive functions. If the weighted sum is 0 or less than 0, it just simply outputs 0. Otherwise, if the weighted sum is greater than 0, then it outputs 1. Remember that a neuron holds a value between 0 and 1, meaning that 0 is fully disabled and 1 is fully activated or lit up. You could probably imagine the problems arising with this. Let's zoom in on an example to understand the caveats of this activation function. Say that a neuron called B has 3 connections from the input layer, therefore having 3 weights. And the weighted sum is just some negative value just right before 0, let's say negative 0.5, which needs to be passed into an activation function. And the step activation function would convert it to 0, which would be okay in our case since there wouldn't be any substantial difference between the weighted sum and the activation value. Say that we know the first neuron in the input layer does not really hold any importance whatsoever, so we decrease its connections weight to a very low negative value, such as negative 200. As a result of that, the weighted sum changes or decreases significantly, but it has absolutely no effect on the activation of that neuron because the weighted sum is less than 0 and continues to be less than 0. Thus, the activation function makes it remain 0 and completely unchanged. Now, say that we get to know the second neuron is slightly more important than before, so we increase it by a very slight positive value, say from a 10 to a 12. Now imagine this change in the weight of that neuron resulted in the overall weighted sum changing from maybe something like a negative 1 to maybe a positive 2. This will have a very small and almost indiscernible increase in the weighted sum, but would dramatically flip the activation of that neuron from a 0 to a 1. So, what I'm trying to convey here is that this step activation function could just light up or completely disable a neuron based upon small changes, whereas big changes could have no effect whatsoever. Remember that an activation function is just a measure of how positive the boundless weighted sum is, but the step activation function is very unstable in this regard. Let's identify the problem, which is that every small change in the parameters may introduce a very dramatic change in the activation. What if we could just smooth the transitions out and make every change proportionally increase or decrease the activation value of the neuron? The sigmoid activation function, also known as the logistic curve, does exactly that. The activation transitions move smoothly in respect to the changes made in the parameters, and it also gently squashes the activation value between 0 and 1. Of course, there are different activation functions which we will explore when we get to the programming part. Now, graphically speaking, the weights will allow you to adjust the steepness of the curve. But what if we wanted to shift the curve left or right altogether? This will come in useful for making the activation function more flexible, as it would have more parameters that could change the output depending upon the scenario at hand, as all parameters are trainable. Let's see what I mean by this and how we can implement this parameter. So this is the sigmoid curve, and the formula for the sigmoid curve is right over here. This curve represents all the characteristics we already know about it, such as the y-axis or the vertical axis represents the squashing of the activation. See how it starts at 0 and it caps out at 1? The x or horizontal axis represents the gradual transition it's making from 0 to 1. Now to shift the curve left or right, say from maybe here to somewhere over here, we would have to add in an extra parameter. An extra parameter will be useful for setting a threshold before a neuron would get, well, meaningfully activated. Or in other words, a bias to the measure of how active the neuron is. How would the bias implement the threshold? Look here. To add this bias, you would add the bias to the weighted sum, where negative x is the weighted sum, before giving it to the sigmoid, thus these brackets. So say we wanted to add a bias of 5. Now when you zoom out over here, you could see that 5 coincides with 0.5, or this is the point where it starts to get meaningfully activated. And you can even add negative weights to make the curve shift leftwards. So now if I add negative 5, you could see that this point where it starts to get meaningfully activated is negative 5, where it coincides with half of 1 or half fully activated, which is 0.5. Each neuron will have a bias value attached to it that will be added onto its corresponding weighted sum before being passed into the sigmoid activation function. If you are still confused about biases, think of it as an extra parameter that allows more functionality, which is the shifting of the sigmoid curve, thus a better opportunity to be more expressive and better, and in turn properly solve the problem at hand. So basically more opportunity for the activation output to be changed according to the problem at hand, as these parameters can be trained. Each neuron after the input layer will go through this process for its activation value, because the neurons in the first layer get their activation values from their corresponding pixel of the input image. The neurons in the second layer pass weights to other layers, with the neurons in those layers having their own biases. So basically, each neuron passes information or communicates with the neurons in the next layer by the weight of its connection to the other neurons. But how can we make it possible? In the next video, I will code a neural network from scratch and invite you to that journey where you can experiment with the code on your own device.